So now we move on into a little bit of recap on digital circuit design. So you're already familiar with all of this, but I'm just going to do a very, very quick recap. So there's largely two types of digital circuits: combinational circuits and sequential circuits. Combinational circuits represent a function on the current input values. So there's the output of the circuit depends only on the defined computation and the input. There's no notion of state that is stored and read, no memory in the circuit. So if the input changes, the output changes. The sequential circuits have memory called state. This is pretty much just to set up a common nomenclature we're going to use in the rest of the lecture. So they have memory, which is state. And the output depends on the current input, as well as what is stored in the state of the sequential circuit. And that's where the name sequential circuit comes from, because the output depends on the sequence of past inputs. So sequential circuit consists of combinational logic and also state information that this combinational logic reads from and writes to. So what constitutes combinational circuits include the input, of course, the output, of course, and also the functional specifications of the, so as a clarification, right now we're talking about combinational circuits. We haven't gone on to sequential circuits yet. So combinational circuits are specified using the functional specifications of the circuit. So how is the output generated from the input, the value of the output depending on the input? This can be defined in many ways, including Boolean logic, truth tables, and some higher level hardware description languages, Verilog, VHDL, Chisel, BlueSpec. There's a lot of these examples. And we have done this in CS151 already. We've already worked with Verilog to design combinational circuits. And one thing that was missing so far is the fourth component of combinational circuits, which is timing specifications. And if I remember correctly, it was kind of hinted during CS151, but I don't think it was fully explained upon. So the timing specification characteristics of combinational circuits describe, given dynamic input, as inputs change over the course of time, how does the output change over the course of time? And this has less to do with the logical correctness of the circuit and more to do with how fast we can make the circuit go. So this is a point of importance for the computer architecture side of things. Right, so we go into the timing specifications of combinational circuits. The first component of the specs is propagation delay, typically denoted using T_PD, as you see on the left here. To put it into words, the propagation delay is an upper bound on the delay from valid inputs to valid outputs. What this means is, if once the input value changes, so this is the input value, the graph for the input value, and below here's the graph for the output value. Once the input bound changes at this red line, how long does it take for the output value to go into steady state of the value that we expect, the output value that we expect from the functional definitions that we gave it? And this propagation delay, and this happens again here. If the input changes again, how long does it take for the output to go into a correct steady state? And propagation delay is one of the biggest factors which restricts how fast input can be consumed. If a particular circuit that we've built and fabricated on silicon, if it has a certain propagation delay, that puts a limit on how fast the input can change. If the input changes too fast, then the output cannot change in time to go into a steady state before the input changes again, meaning the output of this component of this circuit could go either into an undefined state or doesn't change at all. So the switching of the input has to be slow enough depending on the propagation delay of this particular circuit that we've built. So a good circuit would have very low propagation delay because input can change faster. We can process more data more quickly, resulting in higher performance. So the question, I guess, the question for architects is how do we achieve low propagation delay? And before we get to that, there's another specifications of combinational circuit. The second one is what's called contamination delay. Typically denoted as T lowercase cd. Contamination delay is a lower bound. So yeah, it's a lower bound on the delay between the input change and the output starting to change. It doesn't have to go into steady state yet. It's a lower bound on the before the output starts to change. It goes into undefined state. So what this does is it guarantees that the output of this certain module will not change within this time frame, within the contamination delay, regardless of what happens to input. So, and what this means in the grand scheme of things will become clear in a bit, but given an example of an inverter, meaning if the input changes, the output changes to its opposite, the contamination delay would be the time between when the signal changes here and until the output signal goes into an undefined state. And this is a characteristic that either component designers or circuit designers or architects have to optimize for. And before we actually get into how we try to get lower propagation delay and whatnot, here's a little bit of backgrounds on the building blocks of chips, which are CMOS transistors, complementary metal oxide semiconductor. There's of course more newer technologies out there. There are newer technologies that are being researched, but I guess this is the major technology that we're looking at right now. So if you look into a packaged chip, if you cut open its top and look into the silicon, you would get a silicon die. You've probably seen figures like this multiple times on news packets from Intel and whatnot. But if you cut it vertically, if you do a cross-section of this silicon die, you will see something like this. On the bottom, or on the top, depending on how you look at it, you will have the transistor layer, where Intel or other fab plants implement the transistors. And on top of that, or bottom of that, you typically have multiple layers of metal layers on which wires, the connections between these transistors are etched onto. So if you create a logical representation of a digital circuit which connects transistors together, for example, if there's wires overlapping, for example, they would have to go into different layers of these wire layers, of these metal layers. And there is absolutely a limitation on how many metal layers that you can put using current technologies. So if a design has a ridiculous number of overlapping wires, sometimes it's not readily mappable. So there's a lot of research going into efficient mapping as well. And if you go to the transistor layer, there's the transistor. I'm guessing this is representing a transistor built in the 32 nanometer fabrication process. That's why the number 32 nanometers is there. But yes, so beginning from the levels of transistors, this is pretty much the overall picture of what you can find inside a packaged chip. So everything is built as a network of transistors. Transistors on the transistor layer, the network built on the metal layers stacked on top of it. And this is different from a 3D stacked silicon technologies, if you're familiar with something like that. The stacking that you see here, the things that are stacked on top of the transistor layers aren't other silicon layers. Well, they're silicon, but they're not the transistor layers that we are talking about when we talk about 3D stacked architectures. When we do 3D stacked architectures, they're typically, they talk about when we have more than one layer of this transistor layers, which is more difficult to do. Anyways, So using these transistors, the field effect transistors, you can build the logical building blocks. If you remember from CS151, transistors come in two varieties, the PFET and NFET. And these things can be wired together, like an example you see here on the left for a NAND gate using CMOS technology to represent Boolean logic, which represents logic gates. And that's simple enough. That's what we're something that we're familiar with enough. And in the very, very early days of computer architecture, majority of chip design, majority of computer architecture design was actually designing things at the level of transistors. The diagram you see here, something I showed a couple of lectures ago, is the schematics of the Intel 4004 chip, which was the very first integrated chip, IC chip that Intel has built, so it has historical value for them. This was a redesigned version for the 50th anniversary project at Intel. And you can see that the picture might be a bit small, but you can see that it is showing individual transistors. So it was possible to do this at some point in the past. However, before we get into howevers, however, modern chips can't be built in this way. It's just completely untractable. And on top of the actual physical layer, the transistors and the cables and the metal layers, there's another abstraction for building integrated circuits, digital integrated circuits, which is the standard cell library. A standard cell is a library that's provided by the fab plant. For example, if you want to build your chip at TSMC, TSMC will give you their standard cell library for a certain fabrication technology that you want to use. So a standard cell is a group of transistor and interconnect structures that provide a Boolean logic function. For example, inverters, buffers, AND gates, etc. You see a example table here on the bottom. The actual numbers that are being shown here is absolutely not important, except as an example. So there are separate standard cell libraries for a specific implementation technology, specific fab node, vendor, etc., depending on what they have available. They also include physical characteristic information. For example, on the table here, you see each gate type is annotated with a area number as well as delay through this module. And these characteristics are used by the designer, typically a design software, to come up with a performance characteristic, come up with a size characteristic to optimize for the characteristics that we want. So eventually when you design a chip, chip designs are expressed as a group of standard cells networked via wires. So these standard cells are located on the transistor layer in the vertical cutout that we saw just now. And the wires would be routed onto the multi-layers of cables of wires on top of that. And this expression of a group of standard cells and the connections between them is the big part of what is sent to a fab plant if you want them to manufacture your custom chips. And the interesting takeaway from here is that various components do have different delays in areas. Although when we, for example, if we draw an 2-input AND gate and a 2-input OR gate, when we draw the logical diagrams on pieces of paper, they don't look very different. But they do have slightly different delay in terms of when we say delay here, it's propagation delay. They do have slightly different delays. They also take up a slightly different amount of space, just a little bit, on the chip. And when we start comparing things like NANDs and NORs, there are bigger differences. And another interesting thing here is part of the, at least in this example of the standard cell library, they provide an AND4 gate, so a 4-input AND gate. And a 4-input AND gate is smaller than two 2-input AND gates, which is kind of interesting. I mean, it's fairly obvious, but from the digital system design software's point of view, this is another thing that it could be trying to optimize for. So this is an interesting aside. Okay, so now that we have the building blocks, back to the propagation delays of the combinational circuits and how we work with them. So let's say we design this full adder. We take two inputs, A and B, also the carry from the previous adder, and we do this 1-bit addition. A chain of logic components have additive delay. For example, if we have an AND gate and the output goes through an OR gate, the propagation delay through these two components would be the total sum of the AND gate and the OR gate, plus a little bit more as the signal has to travel through cables, but relatively that's much smaller. So from a macro level, the chain of logic components has additive delay, which means the quote-unquote depth of combinational circuits is important. If we can represent this same computation where where one path has 3 logic components going through it, as opposed to say 2 logic components going through it, then the depth is deeper. And it might have a higher additive delay because it's going through more components, more gates. That's not always true because, as you've seen before, the delay of different types of components can be different. So it becomes a slightly more complicated optimization problem. But as a rule of thumb, shallower circuits have lower propagation delay as opposed to deeper circuits. And what is called the critical path defines the overall propagation delay of a circuit. So here we see multiple paths that signals can go through. Okay, I'll just show a drawing here. Among the multiple paths that signals can travel through, the critical path defines the maximum overall propagation delay through this circuit. For example, in this circuit, the longest path any of the input signals can go through to reach the output is through this red highlighted path. And the overall delay of this path is the additive delay between a 2-input XOR gate, a 2-input AND gate, and a 2-input OR gate. And because if there are no other paths in this particular circuit that has a longer propagation delay than this path, then this path becomes the critical path, which defines the overall propagation delay of this circuit. Because regardless of whether S was calculated faster than carry out, we can't provide the next system component that takes the input from this system component doesn't have the full set of input that it requires before both of these signals has stabilized. So the speed, the possible switching speed of this particular circuit is defined by this particular critical path, the delay of this critical path. So this is an important term that we'll be coming back to multiple times in the future, the critical path of a circuit. So far, we've been looking at combinational circuits, and what we've looked at just now was a critical path of a combinational circuit. So we'll go a little bit more deeper into the topic of sequential circuits, partially because combinational circuits on their own are not very useful. You get input, you get output. We don't have memory. We don't have, for example, we can't have programs and whatnot. Sequential logic has state, memory, which is called state. State can be implemented, if you go a little bit deeper into circuits, state can be implemented using things like flip-flops and registers, if you remember them. And these states hold information across signal changes. So state acts as the input to internal combinational circuits. So if you look at an abstract model of a sequential circuit, there are state elements inside the sequential circuit along with the combinational circuits. And the state elements act both as part of the input to the combinational circuit and also as part of the output from the combinational circuit. So the subset of the combinational circuit output updates states and so on. In reality, I guess a slightly more realistic sequential circuit looks a bit more like this. Of course, we won't have a big pool of sequential circuits along with a big pool of memory when we design these things. Due to physical constraints and whatnot, these things are typically interspersed with each other, of course. And an important subset of sequential circuits is the synchronous sequential circuits. A synchronous circuit means all operations are aligned to a shared clock signal. So all input must be aligned to the clock signal. All output must be aligned to the clock signal. So you're probably already used to this notion already. But the interesting caveats of having a single central clock, which all signals must align to, is that the speed of the circuit is determined by the clock speed, as we are used to with CPUs and whatnot, because input can only change at the edges of clock cycles, and that determines how fast the input can change, how fast the output can change, which means how fast can we consume and produce data. But because for correct operations, all paths, meaning the critical path of this sequential circuit, must be shorter than the clock speed, because by the time the next clock cycle begins, if the effects of the previous signals aligned to the previous clock edge has not been fully propagated and, for example, stored in the state, then we will run into an undefined or wrong state of operation. So every single signal path in this combinational circuit, sequential circuit, meaning the critical path, must be shorter than the clock speed, than the clock cycle. So the speed of the circuit is determined by the clock speed, which is determined by the critical path of the circuit. So in order to have correct operation, we need to either have simple enough logic that fits inside whatever clock speed that we have or want to give it, or reduce the clock speed until it becomes longer than the critical path of the circuit that we design. So of course, obviously, it would be best if we can have a simpler logic, a shallower logic with a shorter critical path that that can fit in a really, really fast clock, but that's not always possible. And that's what we're going to be talking about for the next couple of lectures. And that's the major constraint that drives many computer architecture paradigms like pipelining and whatnot. So we've talked with combinational circuits, we've talked about a set of state element constraints, including the propagation delay, not state elements. We've talked about timing constraints, including the propagation delay of a combinational circuit and the contamination delay of a combinational circuit. Synchronous state elements, meaning memory, registers, flip-flops, and whatnot, they also add timing complexities. And these things add more complexities beyond just the propagation delay and contamination delay of these elements. But first of all, state elements also have a propagation delay constraint. So compared to, similar to the propagation delay of combinational circuits, the propagation delay of a sequential circuit defines the time between the rising edge of the clock, because we are now synchronous, time between the rising edge of the clock to valid output from the state element. Contamination delay is for the state element is similar, meaning even after the clock changes, the value should not change for at least a certain amount of time after the clock signal changes. So you've seen propagation delay and contamination delay with sequential combinational circuit just now, but sequential circuits add a couple more constraints. First of all is setup time. We'll get into, maybe I should have put a graphical representation of these things earlier, since this text is sometimes could be a little bit overwhelming, I think, now that I think of it. One element is setup time, denoted as T setup. If you have a state element, it should have holded the correct data for a certain amount of time before the clock edge happens. And the last one is hold time, which denoted as T hold. An input to a state element should still hold correct data for a certain amount of time after the clock edge. And let's go into graphical representations, because I think that will help describe things much better. So if we, the onus of, so we mentioned that these things, setup time, hold time, and all these things are constraints. These are not physical characteristics of, say, system components. So when circuit designers, or when CAD tools, which are computer-aided design tools for circuits and IC silicon, build and optimize chips implementations, setup time, etc., are constraints that these tool chains must meet. So the first constraint that the tool needs to meet is the setup time constraint. Setup time pretty much means, in lay terms, the processing done by this particular, during this particular clock cycle must fit within a clock cycle. So what is happening is that we have a simple circuit here that has one state element where data is stored, and the data from here goes through a certain amount of combinational circuit, and the results from the combinational circuit is stored into the next state element. So let's look at this simple example. And when a new clock cycle starts, the data starting out from the state element 1 must go through all the processing that's required and arrive at the destination state element and reach a stable state, so that data is stored inside the state element before the next cycle starts, and all of this can be started all over again. In mathematical notations, this means the propagation delay of state element 1, so the time it takes from the clock cycle start to the amount to when we actually have valid data coming out of this state element, summed with the propagation delay of the combinational logic, which is the amount of time the critical path for the signal to go through the combinational logic. So adding these two things, along with the setup time of the second state element, which is how long the input to the state element must be holding a valid value before the next clock cycle starts, because it needs some time for this, for the internal state of the state element to change. So the sum of these three terms, how long the time it takes from the clock cycle change to when valid data comes out of the first state element, summed with how long the signal takes to go through the combinational logic, summed with the amount of time the valid signal needs to hold for the data to become safely stored inside the second state element. The sum of these three things must be shorter than the clock period that we have. So once you wrap your head around it, this is a very, very simple notion. I think I just had a really roundabout way of explaining this. So this is the setup time constraint that must be met when we are designing a certain component in silicon or circuits. If this constraint is not met, for example, if the clock speed is too fast for the data to come out of the source state, for the data to do the actual processing, for the resulting computation to be actually stored inside the state element, destination state element. If the clock speed is too fast or the combinational critical path is too long, this results in what is called timing violations. And once you have a timing violation in an important part of your circuit, then you really can't trust this circuit, because it's not going to be doing what you designed it to do. So this comes back to the slide that we talked about just now. In order to avoid timing violations, we either need to reduce the one of these three terms, or all of them, or make the clock speed slower. The other end component is meeting the hold time constraint. And hold time constraint in lay terms pretty much means that processing should not affect state too early. So what this means from a graphical point of view is after we have a clock cycle start, the contamination delay of the state element 1 plus the contamination delay of the combinational logic. So the sum of these two contamination delays must be larger than the hold time requirement of the second state element.
Together, what these constraints mean is that the input data to the second state element should arrive a certain amount of time before the next clock cycle begins. This is the setup time constraint. And the input data to the second state should not change for a certain time after the next clock cycle begins. This is the hold time constraint. If either of these constraints are not met, the second state element may behave in an unpredictable way.
And the real world implications of these things are that it's pretty much impossible at this point in time to meet all these constraints while designing a complex enough circuit by hand. People can't do it by hand. It's something that you really can't do at this point in time. Even once the design becomes even moderately complicated, even something like you can draw on a piece of paper, meeting all of these things at high clock speeds is going to be pretty much untractable. So these constraints are met via computer-aided design tools, which does all the computation, which does all the optimizations, everything for you. So given a high-level representation of a function, it could be in high-level functional descriptions given by a hardware description languages, which could look like C, for example. Or if you give it a functional description expressed in Verilog or something even lower, if you give it a representation given in terms of transistors, CAD Tools will try to create a physical circuit representation that takes into account things like the sizes of the standard cell units, how many layers of wiring that it can do, et cetera, et cetera. The CAD Tools will try to create a optimized physical circuit representations that meets all of these constants so that you can get a high clock speed while getting correct computation. And a rule of thumb here, at least at the level of circuit design that we will be doing, is that meeting hold time is not typically difficult. So making sure that the effects of a previous computation does not reach the next clock cycle too fast is not very difficult, because it's easy for at least at our level of system design to add, say, a bunch of buffers or inverters to add enough contamination delay to the sequential circuits that the sum of two contamination delays is longer than the hold time. This is easy to do. What's typically more difficult is meeting the setup time, which is dealing with propagation delay. All the propagation delay of the source register, the propagation delay of the combinational circuit, etc. All of these things must fit within the high desirable clock speed. And meeting that is more difficult, because that would mean we somehow have to construct shorter critical paths while still maintaining the logical function that we want it to achieve, or reduce the clock speed, which directly translates to lower performance. And of course, we as people taking 152 don't want this, of course. But from the point of view of, say, Intel or other chip designers, this is something that has to be avoided at all costs. So the big question here that we need to answer is, how do we create shorter critical paths for the same high-level logical function? For example, if you want to add two numbers together, is there a way to create a circuit that has a shorter critical path while doing the same operation? And that's the big question that will be answered throughout the rest of this course, pretty much. That's why I love this component of this course very much. This grounds everything in reality. So before we get into the actual tricks, there's this one last piece of background that we want to go into, is placement and routing. So placement and routing is something that is done by the CAD software. It's not something that we do as people. And placement and routing is kind of a nuanced thing, but from a 100-mile high point of view, it involves mapping state elements and combinational circuits to limited chip space, because we're not going to have unlimited chip space. Of course, even if we did have unlimited chip space, using more chip space directly translates to more cost. So minimizing chip space is good. This is also done via CAD tools, like I said. Compared to a logical representation of a combinational circuit, once you do placement and routing, this may add significant propagation delay to what you previously had. Because when you consider, say, a circuit path that consists of a path which consists of 3 AND gates, you can pretty much just add 3 propagation delay for the AND gates together. But because of some placement and routing restrictions, if these AND gates are located centimeters apart, for example, then the propagation delay of these copper wiring, silicon wiring, becomes significant as well. To put things into context, speed of light, let's consider speed of light, and let's consider a CPU clock speed of 3 gigahertz. The amount of space that light can travel during a single clock cycle, a single 3 gigahertz clock cycle, is approximately 10 centimeters. So if you have a chip, a hypothetical chip, which has a silicon die in it, which is a 10 centimeter silicon die would be huge. But say if you have a 10 centimeter silicon die, and due to some perverse restrictions in placement and routing, you want to have a combinational circuit that connects one piece of circuit from one end to the other piece of circuit from the other end. Regardless of how shallow your logical representation of the circuit is, regardless of whether it does nothing, if it just has a buffer or anything, the propagation delay for that path is going to be longer than the clock speed, because it's just a physical limitation of our universe. Light can't travel 10 centimeters. It travels 10 centimeters over the course of a clock cycle. No signal can travel faster than that. Yes, we're going into physics now, which is cool. So here's an example of how that can happen. Of course, there's many examples, many different cases that may call for something like this. So let's look at a sequential circuit described here. And let's say we have complex combinational circuits, 1, the green cloud here, and 2, accessing a shared state A, which you see here. And we can also have a complex, or maybe less complex, combinational circuit 4, also who needs to access A. But say if 1 and 2 are too large, and the CAD tool tries to put 1 and 2 together as much as possible, because they're all accessing the same state element, and the distance between the state element and these sequential combinational circuits are going to affect the propagation delay between these things as well. So the CAD tool will try to put these things together, physically put these two things together as much as possible, which could mean, for example, if the combinational circuit 4 could now be pushed a little bit away to be farther from the register A that it wants to access. As a result, the path from the combination state element B through 4 to A has now become very long. So this could be, this is kind of a contrived example, but this is a simple case of when placement and routing by the CAD tool may add significant propagation delay to what was a simple addition of propagation delays of these logic gates. So this is kind of an aside. may not become too important for us yet. But the rule of thumb when we're dealing with these kind of things is that one combinational circuit should not access too many states, whether it's wants to read from too many states or whether it wants to write to too many states. It needs to avoid doing this as much as possible. And of course, on the flip side, one state element should not be used, whether it's read or written to, by too many combinational circuits, because if a lot of these things have large fan outs, then all of these things need to be grouped together as much as possible by the CAD tool, which could result in these complicated issues. So to tie this back to computer architecture a little bit, we can look back to one of the questions that was posed in one of the earlier lectures. Why are register files, at least RISC-V and things like MIPS as well, why are register files 32 element? Why not 1024 or more or less? Why not less is a simpler answer, because data-driven design has told us that having more registers typically do improve performance if compilers know how to use it well. But the answer to why we don't have more than 32 elements is circuits in physics. So if you look into a register file, which stores the 32 registers, and depending on the write select or read select signals given by the rest of the circuit, depending on which register file register it wants to write to or read from, it needs to have a multiplexer and a demultiplexer to one, use a demultiplexer to send the data we want to write to the correct register and not overwrite anything that we don't want to. And we also need a multiplexer to take forward the data from the correct register that we want to read from. And multiplexers and demultiplexers, if they need to happen within a single clock cycle, is kind of expensive in terms of propagation delay. Because if we want to build a wider fan-out multiplexer, we need to hierarchically organize smaller multiplexers into a tree. And this absolutely of course, the propagation delay of these multiplexers would absolutely be additive. So the short answer to why 32 elements is, again, a balancing act of data-driven design. If the compiler knows to optimize, if the compiler knows to use these 32 elements well, the register file well, performance kind of, I wouldn't say plateaus maybe, but it does reach a knee somewhere around 32 elements. I don't have the reference here right now, but there was a paper that described this. We do reach a knee around 32 elements. The performance improvements after 32 elements become kind of not as steep as before, whereas the impact on clock speed and circuit complexity due to these deep multiplexers and demultiplexers become more prominent as we go beyond 32 elements. So 32 elements has been chosen, at least at that point in time, because as a good balance between having more registers and having less propagation delay. So that is very cool. In my mind, this is one of the coolest things that we're doing. Yes, and to give a real world example, back in 2002, when CPU frequency scaling was still going strong, when we were reaching multiple gigahertz of clock speed for the very first time. But of course, at the time, the FAP technology wasn't as good as what we have right now. So the transistor sizes on these chips were much larger than what we have, which means longer propagation delay for each circuit component. So higher clock speeds, but longer propagation delay. So having a multi-gigahertz, very, very high clock frequency with larger transistors meant according to their benchmarks, the setup time constraint, the propagation delay constraint, could only tolerate up to 8 inverters in its critical path. So something like 8 sequence of transistors in the critical path. And this is a really, really stringent restriction. If you remember the 1-bit full adder that I showed as an example a couple of slides ago, the critical path there was 3 logic components, XOR gate, an AND gate, and an OR gate. And that's already pretty much filling up the whole budget of the critical path. The 8 inverters critical path is pretty much already taken up by that single 1-bit full adder. So can we even fit a 32-bit adder in here? We cannot, because the whole time constraint, setup time constraint, is way too strict under these restrictions. However, even under these restrictions, we've had complex processors. Back in 2002, we had Pentium 3s, Pentium 4s, multi-gigahertz things that were running very, very complicated logic. And the question is, and the big question, the central question to this whole course is, how do we pull it off?